Talking about the spontaneous processes in 19.1 in the first law of thermodynamics. And if you remember back from chapter 5, energy cannot be created or destroyed. This is kind of the basic fundamental premise that the total amount of energy in the universe is always constant. So that's kind of the truth that goes along with the first law of thermodynamics. However, we learned that energy can be transferred from a system to the surroundings or vice versa. If you remember back whenever we discussed enthalpy and we think about a system, if we have energy that moves out from the system to the surroundings, the total energy is not just created or destroyed. The only thing that happens is it gets transferred out. So this would be an example where we talked about delta H referring to the system. That enthalpy is going to transfer out and the system is going to become exothermic. The surroundings are going to gain that energy and become endothermic. So we talk about isolated systems or chemical equations that we talk about and isolated equations. We're going to talk about this in terms of spontaneity as well. Vocabulary word-wise, a spontaneous process is one that can proceed without any outside intervention, wants to happen on its own. A couple of examples of that is a gas. There's a figure in your text that I think that's helpful that looks at gases in general and how they look to the observer for spontaneity. If you look at the gas in vessel B will want to move into vessel A, but once the gas in both vessels, it will not spontaneously return to B. So let's kind of walk through the process here. So right now it's closed. There's no atmospheres of pressure in flask B. All of the gas is present in flask A. So if we close the stopcock, there's going to be no flow at that point. As soon as I turn this stopcock open to let the gas flow, notice that the process goes from A to B and some of the gas flows in. Since I didn't have to do anything else except for to open the stopcock, this would be considered a spontaneous process. However, when you think about happening from B back to A, this is not going to be spontaneous. We're not going to get any flow from B to A. That's a non-spontaneous process. So thinking about the difference between spontaneous or non-spontaneous, spontaneously means it goes on its own without any outside intervention. Non-spontaneous means that it's not going to happen that way. Usually, in general, kind of the rules of thumb with spontaneous processes that are spontaneous in one direction are not spontaneous in the reverse. So in this previous example, when we thought about the flask, since it was spontaneous from A to B, so we said A to B was spontaneous, then the other direction from B back to A is going to be non-spontaneous. And that's typically true of most chemical reactions as well. So what does this mean, this idea of spontaneity? How can we tell if something is a spontaneous reaction? How can we tell if something is a non-spontaneous reaction? Sometimes it's dependent upon temperature. Sometimes it's spontaneous at one temperature and not the other. Typically we're going to see T with a capital T, and what that means is we're going to have to deal with Kelvin. So Celsius to Kelvin conversions are a must. An example of this, if it's above 0 degrees Celsius, ice will want to melt. If it's below 0 degrees, and it will be spontaneous. If it's below 0 degrees Celsius, the ice will not melt. The reverse process, if you get below 0, then you're going to get a freeze. So spontaneity can't be temperature controlled. This is a good time probably to review the difference between state functions and non-state functions. There's 3 of them. We talked about these back in chapter 5 as well. Temperature, which is the average kinetic energy of the system. Enthalpy, which is talking about the energy at specific pressures. Internal energy, talking about the energy inside like Q. Those are state functions. And a state function doesn't depend on how the state is reached. It just depends on what it is total. Q and work, those are not state functions because those have processes that have to happen to give us the total Q. It does matter the individual steps. Temperature, enthalpy, and internal energy, it doesn't matter how they got there. It's just a measurement of what it is at that particular time. So the next topic is talking about processes that are reversible. We talked about equilibrium in the last chapter. And this kind of continues on with the idea of equilibrium and spontaneity. If a process is reversible, the system changes in such a way that the system and surroundings can be put back in their original states by exactly reversing the process. This figure does a really good job of showing how this works with my systems and surroundings examples earlier. Notice in this picture, the system is at a higher temperature than the surroundings. So notice that T, positive, the T in the outside, we're going to release some of that temperature out to the surroundings. So small increments of heat are transferred from the system to the surroundings. Now, if we lower the temperature, then some of that energy, some of that heat is going to transfer back from the surroundings back to the system, depending on temperature. These two processes are reversible. Now, they can be spontaneous between the two of them if we can reverse them exactly and we change the temperature. So when you think about it, it's like equilibrium, but it's temperature and that can change this. So think about in terms of like our water example earlier. So again, the total energy never is created or destroyed, but it can transfer from one to the other. A reversible process, if it can go back and forth like the previous example, a reversible process cannot be undone by exactly just reversing the change to the system. So that means if I try to change the temperature and nothing happened, it's not reversible. You have to do exactly what you did to the first process and then do the exact opposite of that for it to be reversible. If you can't do the exact same change in the opposite way and get it to go back, it's not reversible. What we did up here at the top, this example, that is reversible. Now, if we change the temperature and it didn't go back to being in its original state, then that's irreversible. So when we think about a spontaneous process in general, they're usually irreversible. That means once they go there, you can't get them back. A good example is when you take an egg and I hold it above the ground and I drop the egg is going to hit the ground, it's going to shatter and break, you can't get the original egg back. Did the egg spontaneously fall to the floor and crack open? Sure, but you're not going to get it back. That's an irreversible process. What we talked about with the ice melting and freezing, that's a reversible process. Spontaneous processes are typically irreversible. An example of that is a figure in your text that talks about moving of gases. Kind of explain what we've got. We've got a vacuum that doesn't have any air in it. We have the piston that's going to push down. We have a gas inside of this, and that partition moves back and forth. The irreversible expansion of gas, there's no work done on the system right now because work is that force times distance. We pick up that partition, all of that gas wants to expand. The gas does work on the piston because it applies a force over a distance. There's compression. We've got work done on the system is greater than 0. So the spontaneous processes are irreversible. Once they go there, they're there. If you think about this, there's work on the piston, work is done, we've got irreversible. You can't do the exact same change to it and get it to go back the way it was. We have to add more fuel into the chamber or more air to make this happen. So spontaneous processes are irreversible. When we have reversible processes, we typically have equilibrium. And equilibrium does relate to the free energy like we discussed in the redox chapter. But again, spontaneous processes are irreversible. Typically, they cannot be undone by exactly reversing the change to the system. If I just take this gas and I take it out of it, we're not going to undo and put it back in its original state. That makes it spontaneous, occurs on its own. So reverse processes sometimes can be spontaneous if we change the temperature, but in general, spontaneous processes are typically irreversible in this case.